Hello, and welcome back to CS631 Advanced Programming in the Unix Environment. This is week 5, segment 3, and after we covered the general functionality of a compiler in our last video, we'll now take a look at each of the different stages in practice. Remember, a compiler is a tool, or rather, as we'll see in this video, a set of tools that turn programming language source code into an executable for a given machine architecture. Isn't it nice to have a helpful mustachioed fella like this to help you out? So let's take a look and see what's inside our little friend here. As we mentioned in our last video, a compiler actually performs a series of steps, which in the case of the GNU Compiler Collection, or GCC, is itself broken up across multiple standalone tools. There's preprocessing, compilation proper with all its lexical syntax and semantic analysis, assembly, and linking. Preprocessing, as we briefly illustrated, takes our source code and expands it according to certain rules. Let's now illustrate this in detail and by example. Here we have a file hello.c that looks like so. We are calling func1 from main, func1 calls func2, and func2 simply calls printf. This will then inform us about which particular food item is especially delicious. We're using the preprocessor directive if&def define to illustrate how CPP may expand this code. Okay, so first let's just compile it using cc. There. Now we know avocado is great on anything. Good. This is because we had not provided a definition for food, so the default definition was used instead. How did cc do that? Let's take a look at the manual page. Here we see confirmed what we had previously mentioned. The compiler performs the different steps in order, using different input files at each stage. But we had also mentioned that preprocessing is actually performed not by cc, but by the cpp command, the C preprocessor. CPP is automatically invoked by cc, as noted here. So what does that look like? Here, let's first display our source code with line numbers. We see preprocessor directives on line 21 to 23, as well as on line 19. Now, let's run CPP. There. Okay, that's a lot of output all of a sudden, but our basic C code remains in place. Now, let's scroll up a bit, and we see a whole lot of code that we never wrote. These lines are, as you probably recognize, the forward declarations of the various functions from the standard I/O header file. See, over here we have printf, for example. Let's run this command again and start at the top. The C preprocessor tells us which files it's reading, and then shows us that on line 19 of hello.c, it then pulled in the file user include standardIO.h, which in turn appears to have an include statement on line 40 for cdefs.h, and so on and so on. So in this way, the preprocessor iterates through all the files and pulls in whatever is found in those headers. And so we then get the various type and function declarations here. We can instruct CPP to leave out the annotations using the -p flag, and the output then looks like this. Typedefs and structs and function prototypes, and finally our original C code. Hello.c is obviously a C source code file. The output of the C preprocessor, stored by convention in a file ending in .i, is also C source code. But the difference here is that hello.i contains a lot more C code. It contains all the code included from the header files, so it's an easy 10 times as large. So now, can we actually just compile that .i file? Let's give it a try. Yep, that works. Okay, so far so good. Now we know how the include statement works. What about the define statement? Note that over here our output of CPP no longer contains any if-def statements, and instead we see the bare string avocado over here. What happens if we define a different food? Let's say tomato. Look, there it is. But note that this is a bare word, not a string. We need quotes here. Let's try again. We need to escape the quotes here, since our shell would otherwise eat them when it processes the command prior to execution. There. So, let's see what the difference is between our original and this output. There, just that one word. But do note that we did indeed replace food in place at preprocessing time, prior to compilation. That is, we are changing the actual source code and replacing any occurrence of food with tomato. This simple replacing means that whatever we define needs to be syntactically correct anywhere it appears, which is why we needed to include the quotes in the definition. Okay, so now this will produce a program that says tomatoes are great on anything. But we never invoked CPP before, we always only ran CC. Can we see what CC does at each stage? There. If we pass the -e flag, then CC will stop after invoking CPP. Yep, that looks just like before. Now let's add the -v flag to the compiler, so it shows us exactly what it's doing. We'll ignore the actual output and just look at the compiler's messages. When we add the -v flag, the compiler shows us all the details about the execution, what version, how it was built, etc. It also shows us the compiler flags it used to run, and there we see that it will use -e as we had asked it to. But note that it also uses -wall, -werror, etc. We hadn't specified those. Where do those flags come from? Well, remember when we had set up our virtual machine, we had configured our shell to use an alias for CC? And we had also added some default C flags to our environment, to ensure that whenever we run CC, it would use those flags. So that's where those come from. Let's just unset those for the moment. Yep, there we are now, without any of those flags. Except there are some flags we hadn't specified, which appear to be default or built-in for this compiler. This allows the compiler to use machine-specific options to optimize the code by default. But okay, so we run with -e, and our preprocessor now has to find the included headers. For that, it uses this path over here, meaning when it sees include standard.io.h, it will first look in this directory, and then under user include. Okay, so avocado great on anything, we know. How do we get that to change again? Just like CPP, the compiler also takes a flag named -d, so that the following will work too. Now, once more in verbose, we see the compiler performing all steps, invoking the preprocessor implicitly, and then performing compilation and code generation into a temporary .s file under /temp. It then invokes the as command on that file to create a temporary .o file, and finally invokes the linker ld to create the executable. Okay, so we observed the first stage of the compilation process, preprocessing via CPP. We can manually invoke the preprocessor ourselves if we like. It will produce C source code without any preprocessor directives, suitable to be compiled and by convention written to a file ending in .i. We saw that we can define macros or values using the -d flag, both to the preprocessor or to the compiler driver cc. That means that some flags passed to cc may be passed through to the different tools it might invoke. We'll see other examples of that in future videos. Finally, if we want to observe exactly what the compiler does, we can pass the -v flag. When doing that, we saw the different stages and different tools invoked as noted above. Now, after having covered the preprocessing stage of the compilation process, we'll move on to the compilation and code generation. So stay tuned for our next video in the series. Until then, thanks for watching. Cheers!